Great. Good afternoon, everyone. Thank you for coming back after lunch. I hope I can keep you awake. Thank you, Thomas, and the whole team for putting this on. This has been a very exciting day and a half so far for me, and I've really enjoyed it. And thank you for the introduction. I don't deserve it, so but I will do my best to live up. So my name's Andrew Glass. I work at Microsoft, and as was mentioned in the introduction yesterday, a lot of us here, including myself, actually wind up spending our time doing this this is kind of a spare time activity for many of us, and that's true of me also. My day job has moved from shaping, which it was 15 years ago, into other things. And so those other things, my hobbies really, are now trying to make sure that ancient writing systems are equally supported. So I look after these sort of a digitally disadvantaged community of scholars who work on these ancient systems. More about that in a moment. To sort of key into the theme of this conference and of Unicode itself, this idea that we can render any writing system on a computer is something that speaks dearly to me. And what I try to do, I'm a very practical person. I see a problem and I want to fix it with existing technologies, because if I wait for the future technologies, it could just be a dream that doesn't happen. So I think of myself as kind of a dongle. I try to look around and plug in dongle to dongle to dongle to see what we can do in order to connect this device or this writing system into a supported future. So this was kind of my mental map of where I wanted to go with this talk, and I realized this is after lunch, and also I wasn't quite clear that I want people living in my ideas or in my mind. So I thought, how about we do something that isn't me, and dress it up as a seasonal calendar with only 6 days. So in the first space, I want to talk about glyphs. And a font, of course, is a collection of drawings. And these drawings, mostly today, are vector outlines. And so the first pitch on universality is that the visual system of a writing system can be captured and represented with a vector outline. And so whether your vector outline is the letter G, or whether it is something more complex, the ability of a vector outline to contain a shape and put it inside a rectangle is central here. So it could be the Mona Lisa. You could have a color SVG of the Mona Lisa. These exist. And that could be your font glyph. So there's incredible, probably, practically speaking, infinite capabilities of vector outlines to render the visual elements of a writing system. Important here, I've put a Unicode code point here, and I've put the name of this glyph. This is G. This name exists in the open type space. So in addition to being a dongle, I think of myself primarily as an open typer. We've heard from type designers, typographers, historians. The open typers, I feel, are represented too. It's a small community. But there are some greats that I've learned from in the audience. So the other thing that we can do in order to reach beyond, if we just dealt with glyphs, we've got 65,000 as our maximum. And that's okay for a lot of simple writing systems. It's maybe not okay for a full, complete Chinese font, but we're talking about practical solutions to using today's technology. And for Chinese, you're not doing complex shaping across the entire range of glyphs across 104,000 code points. Maybe Ken is, but I'm not. And we can adequately represent Chinese with multiple fonts. So 104,000 characters, but 64 limit for glyphs. For positionings, we've got the base glyph, we've got an anchor point, we've got another glyph for a mark, and we can put them together arbitrarily. And this really is a multiplier in terms of what kind of combinations we can come up with. Tibetan does this really on steroids. It has mark-to-mark positioning. You've got about 15,000 base syllables in Tibetan. You actually can produce them with multiple visual elements, but one of the multipliers for Tibetan is this ability, and it's legitimate in the writing system within the script grammar. You take the vowels from an extended phrase and you abbreviate it down to a single syllable or a reduced number of syllables, and you take all of the vowel marks from subsequent terms and you stick it on one of the key elements. So this is totally legitimate, and it amplifies your 15,000 up a bit. So let's call it round about 100,000. And we heard yesterday actually doing cursive attachment in Arabic with just 4 basic forms. Somebody had a sample of about 100,000 samples. So this is the range that we get into with cursive attachment. Let's talk about substitution. Code point, it's got a Unicode code point, another one with a Unicode code point, and it substitutes to something that doesn't need to have a Unicode code point. In this case, FI has a Unicode code point, but it doesn't need to have one. And this is really our most productive element for OpenType. We can substitute in a myriad of ways, and these are quite familiar. So one of the extreme cases of this is Old Hangul. You have here a sample Old Hangul glyph. The encoding system for Old Hangul allows for 1.6 million different blocks. Most of those will never exist in text, but as you know, in our contemporary time, we do not know what old manuscript will be discovered and therefore need some additional block that hadn't been thought of before. And so I see our responsibility in the OpenType space especially, but also in type design, to anticipate and generalize the model of the script grammar so that we can productively create the forms that are needed, might be needed in the past that we then come to learn about, or could be needed in the future. So the other type of character that is really important in the tool chest of somebody working on OpenType is these control characters. These are things that need not have a visual form, but they have a visual function. And this is zero-width non-joiner, or affectionately called a zwinge. And this one has the effect in this context of breaking a Western Syriac term and doing breaking that join. Obviously, that's not a legitimate use of it. I don't know Western Syriac, but it shows the effect of that control. So on the left side, you'll note we've got a glyph. It's got a code point. On the positioning, I had 2 glyphs. They both have code points. And in the third case, I've got a control with the code point. On the corresponding, on the right-hand column, we have a glyph without a code point. So we're doing substitution from things that are mapped in Unicode to things that are not mapped in Unicode. Oh, here's Mongolian free variation selector. Let's skip that one. You know your encoding is in trouble when you need things called free variation selectors to get the desired visual outcome. As I said, we can represent any writing system with existing technology, but we can improve it. And so we could talk about Mongolian some other time. So let's talk about this. We're talking about positioning without code points. And I think I owe the origin, the inspiration for this to, I think it was actually Kamal that originated this technique. This is called a hanger. It is an empty, invisible glyph. There's no visual form. There's no vector outline in there. It has a name. Name it whatever you want for your particular project. But it has anchor points. And you can use this in order to position other things. And so this is really a truly productive and powerful tool when it comes to reaching from where we are with maybe a limited number of signs into a very adaptable system. We'll come back to that in a moment. An example of how we use this, I've been working on Egyptian, and this ability to use things that don't have a visual form but have a positional relationship is absolutely critical to how you build up an Egyptian block. And then also we saw it this morning with Mayan, how you position arbitrary glyphs relative to each other in a structure that is determined at the point of text input. So the final box, in case you hadn't guessed already, is going to be functional things on the left column, but that don't have code points. So these are unmapped functional things. And so an example of this is these H0 through H6. So to think about this a bit more, let's go over to Bedard, who's really one of the legends of OpenType and text rendering. One of the really formative moments for me was his presentation back in 2015 at the Unicode conference, where he showed with a fantastic presentation. I encourage you to snap this QR code and look this up online and watch the video. He showed that OpenType is Turing complete. So going back to the origins of my talk, this is universality that we're talking about. We're looking for both visual universality at the level of SVGs and glyphs, but we're also looking for logical universality to make sure that the two components, the visual system of a writing system and the adaptation, the dongle that is going to connect our Unicode encoding, the agreements that thrashed out in the process of working with the writing community through the script ad hoc committee with Ben Yang and Manish and many others. That process is glued together through through the capabilities of OpenType. Now, it's okay to say, okay, in theory, Turing complete, great, we can do anything. But in practice, we have these limits. We have 65,000 glyph limits. We have a limited number of lookups. I think it's also 65,000. Each of these lookups has a limited length of 6K or something like that. And so there are all of these limits that constrain what we could do universally. In the Turing models, of course, he has an infinite tape. We do not have infinite tape with OpenType. So a key question for me was, how is OpenType sufficient to render something as complex as Egyptian and to do so within OpenType? And I put it to you that the answer is yes. So here is the Rosetta Stone. This is completely compliant Unicode rendered in a browser using HalfBuzz. Thank you, HalfBuzz, for updating. Ned also assures me that, that Safari and Cortex are updated. So we updated to Unicode 15, adding additional Unicode code points to support Egyptian format controls. One of the subtle ways that you can see that in this particular edition is that this down here in line 12, we begin the cartouche without a cartouche opener. So we can invoke the cartouche on demand so that if the front of the cartouche was damaged, then you can do the right thing by the text and have it display. Let's have a zoom in here. The way that this Egyptian font works is that we have a grid at 6 by 6. We were using the same grid of 6 by 6 with Mayan. Whether that continues to be the basis for Mayan, we shall see. But it works very well for Egyptian. Any sign, and there are 1,000 Unicode signs encoded, there are 1,000 Egyptian hieroglyphs encoded in Unicode today. There are 4,000 more coming. The model for the OpenType for Egyptian allows up to 16 Egyptian hieroglyphs to be clustered into a single cluster and arranged arbitrarily with horizontal and vertical insertions. You can see the cobra inside this cartouche with the ankh. You can put things in corners. You can put things inside of each other. You can put things inside of things So the possibilities here are really astounding. We have effectively 1,000, I think, to the power 16, which is an incredible number of variation inside a single code block. So I wanted to show you an example of how this works. The Egyptian font has about 1,300 lookups. It is by far the most complex font that I know of in terms of OpenType projects. The most complex script that we ship on Windows today is Telugu, and it has 200 lookups. And so going to 1,278 with Egyptian is a really big update. The font still compiles. Amazingly, it is very performant because it is on a system that uses the graphics processing unit, the GPU, to render the text. All of those instructions seem to be parallelized, and so you wouldn't notice that you're actually doing 1,200 lookups per character on the fly. So that rendering of the Egyptian, of the Rosetta Stone, it loads almost instantaneously. So it is all backed and powered by this ability to program directly in the OpenType. And so here's an example where we need to count how many horizontal joins we have inside of a block. We take the joiner character, that's a visible control, that is a control that has a code point, and we inject some token. It's got an H0 token. Name is just something that's convenient for me, but it's called H0. It has no deep meaning beyond that. And at a block, you have one H0 and injected at the beginning, and then lots of H0s injected after that. And so there's a simple substitution that says, in the context of 4 following H0s, then make this H6, and so on down to the last one, which is H1. And when the effect of this H6 is now I know that I've got how many columns are in here. So you can actually do mathematics. You can calculate the width of all of the pieces in this in a cell. You can calculate all kinds of things that go into this, including offset spacing and a range of things that are required to display the Egyptian correctly. Not only that, you can do all of the right to left, and you can do the vertical as well. So in this is the font rendering in Chromium. It is a cartouche now rendered vertically. The glyphs, the blocks are not rotated because that's the style for Egyptian, but we can still cluster and compose that block correctly. And you'll see that this is now the right to left form. So we are doing vertical right to left, vertical left to right, and right to left, all in a single font. And in a sort of an Oprah Winfrey moment, the font is available as of this morning. It's not under your chair. But you're welcome to grab that QR code and download a copy of the font. It's open source, and I hope we will treat this as a reference version for people with better typesetting typographic skills than me to actually create some beautiful Egyptian fonts. Yeah, thank you.